All right, here's our second video on improper integrals. These integrals are improper not because the bounds of integration involve an infinity or a negative infinity. In fact, if you look at these two examples that I have written up here, at first glance they look pretty normal. Like they kind of just look like problems that you've been able to do this whole term. But if you investigate a little further, you see that there's something wrong with each of these problems that make them improper, and it has to do with discontinuities. So what I'm saying is if you go back to 5.3 when we first learned the evaluation theorem, I didn't read this very carefully for you. All I told you was kind of this part of it, right? If you're trying to figure out a definite integral, all you got to do is figure out the antiderivative, capital F of x, and then plug in the two bounds, a and b, and subtract them, and you're good. There's this magical theorem that always works, and I totally neglected to mention that it really only works if your function is continuous on the closed interval from a to b. So everywhere between and including your two bounds here. And I didn't mention it because I knew that I would only give you questions for which this was satisfied, so you didn't really have to worry about it. And you're like, whoa, you kind of lied to me. You didn't give me the full story. Well, I also knew that 5.10 was coming up, and in 5.10 we would talk about cases in which the function in question wasn't continuous on this closed interval, and what you do in those cases. So two different examples. This first one here, what's going on here is this thing is discontinuous. I don't even know if that's the right word to use. I think that is the right word to use. It's undefined anyways at one of its endpoints, at 0. Because the natural log of 0 is undefined, x times the natural log of x is undefined at 0. So it doesn't fit this criteria, right? A is 0, and our function f, which is x natural log of x, is not continuous on the closed interval from 0 to 1 because it's undefined at 0. It would be continuous on the open interval from 0 to 1, or open on 0 and closed on 1, or something like that. Any of that would work, but technically it doesn't fit this definition. So what do we do to fix that problem? We cheat, I guess, informally speaking. We're like, no, I don't want to know about the integral from 0 to 1 of x natural log of x because I couldn't use the evaluation theorem for that. What I'll instead wonder about is the interval from a to 1 of x natural log of x. And as long as a is a number greater than 0, then my function will be continuous on the closed interval from a up to 1. And you're like, wait, but you don't want a, you want 0 here, right? Well, we can kind of cheat. We can take the limit as a approaches 0. And in this case, we're going to approach 0 from the positive side. And the reason we're going to approach from the positive side is in order to keep this continuous, we need a to be a number slightly greater than 0. You can kind of think about it this way. We're going to get infinitely close to 0, but we're going to come from the positive side. If we came from the negative side, we'd be slightly less than 0, and we'd be containing that point 0 in this interval. And if this interval right here contains 0, then we have a discontinuity in our interval, and we can't evaluate the integral. It's hard to say interval and then integral one after another. We can't evaluate the integral using the evaluation theorem. So here's our little trick. It's kind of like you saw in the last video. All you do is you put in a constant, evaluate things, and then when you're done, you're not done because you have to evaluate a limit at the end. And how do you evaluate this? Well, the same way we've been doing it. Figure out the antiderivative of this guy. In this case, the antiderivative isn't really easy. You could try thinking about the different methods that you have. I don't think you can use it with any of the basic methods. Use substitution, that ain't going to help. What about integration by parts? Right? Or maybe if you're not just going down the checklist, you think integration by parts naturally because we have a product of these two different functions. So I want to make one of these u and the other one dv. And here's where it's tempting to make this your u because that'll simplify things so nicely if this is your u. But you don't want to make this the u. You instead want to make this the u. And the logic for making this the u is the derivative of this guy is 1 over x, and it'll go really nicely with the antiderivative of this guy. So thinking integration by parts and letting u be the natural log of x, and therefore by process of elimination, dv is x dx. All I got to do is figure out du and v. And I don't think either of those are too bad. The derivative of natural log of x is 1 over x dx. And v, in order to make dv equal to x dx, is the antiderivative of x. So if you think about this as x to the 1 power, the antiderivative would involve x to the 2nd power, but we need a 1/2 out in front to make sure that the coefficient ended up being the one that we need. With these 4 parts, we can apply our integration by parts formula. Maybe you have it memorized, maybe you don't. The integration by parts formula says that the integral of u dv equals u times v minus the integral of v du. And I'll leave my bounds on this integral, and maybe I should point out that I still need to evaluate this function from a to 1, but I won't worry. This will remind me that I have to do that later on. I don't know if the notation's great. I've just never learned a better notation to write this up in. And then going through the same steps that we learned in the integration by parts video, I guess we take the 1/2, pull it out in front. So that's this 1/2, and then 1 over x times x squared is just x. And so I still have to take the antiderivative of this thing. But that's really easy because we kind of already did it up here, right? The antiderivative of x is the 1/2 x squared. So I can just replace this x with a 1/2 x squared. And you're like, careful, you wrote 1/2 twice. Nah, this 1/2 is here. And then this results in a new 1/2 that I wrote right next to it. This will eventually need to be evaluated from a up to 1. And I don't know, you could probably just evaluate it the way it's written. You could also try to simplify it first. I'm not even sure what will make it easier. My gut instinct is to pull out a 1/2 x squared from both terms. And then what I have left over here is the natural log of x. And then what I have left over here is 1/2. And then evaluate that entire thing from a to 1. So let's see what happens here. If I plug in 1s, the natural log of 1 is just 0. And 1 squared is just 1. So I get 0 minus 1/2, or negative 1/2 in here. And then I get 1/2 out here. So 1/2 times negative 1/2 is negative 1/4. And then from that, I have to subtract what I'd get when I plugged in a's. And when I plug in a's, I would get 1/2 a squared times the natural log of a minus 1/2. And then this limit's kind of a mess, but maybe we can figure it out, although I think we might need some more advanced techniques for evaluating this limit. We can try to just look at it and see if it's obvious. Let's see if this a gets really, really close to 0. This gets close to 0, this whole term. Well, that'll be nice, except that the natural log of a gets close to the natural log of 0, and the natural log of 0 gets close to negative infinity. So I kind of end up with a 0, informally speaking, times an infinity, informally speaking. This is going to be an indeterminate form. And so what I'll have to do is use L'Hopital's rule for this. So what I can do is I can think about this limit as the limit as a approaches 0 from the positive side of negative 1/4 minus the limit as a approaches 0 from the positive side of the rest of this stuff. When I have the limit of multiple terms, I can figure out the limit of each term individually. So I got negative 1/4 minus, and I can also pull this 1/2 out in front of the limit, and that's a result of the limit laws that you may or may not have learned in Calc 1. And just evaluate the limit as a approaches 0 from the positive side of a squared natural log of a minus 1/2. And then this thing, maybe I have to use L'Hopital's rule on, but it's not really in a great form to use L'Hopital's rule at the moment. So maybe I can clean it up a little bit. Tempting to do negative 1/4 minus 1/2 and call that negative 3/4, but you can't because this negative 1/2 is being multiplied by this limit, whereas this negative 1/4 is not. A couple different ways you could write this as a fraction, but I think what makes life easiest is to write it as the natural log of a minus 1/2 divided by a to the negative 2 power. And then I can say this equals, using L'Hopital's rule, negative 1/4 minus 1/2 of the limit as a approaches 0 from the positive side of the derivative of the top divided by the derivative of the bottom. The derivative of the top works out pretty nicely. It's just 1 over a, right? Because the derivative of two different terms, you take the derivative of each term individually. This is a 0, and this is 1 over a. And the derivative of the bottom, you use the power rule to bring this exponent down in front, and then subtract 1 from the exponent to get negative 2a to the negative 3 power. And then if you kind of think about this as a fraction over a fraction, we can make the bottom here negative 2 divided by a cubed, because a to the negative 3 is the same as a cubed in the denominator. And that negative 2 over a cubed, we can multiply up top. And so you can sort of picture 1 over a times negative a cubed divided by 2. And when all the dust settles, you get negative a squared over 2. But we're taking the limit as a approaches 0 of this thing. And when a gets really close to 0, 0 squared is 0, negative 0 is 0, 0 divided by 2 is just 0. What I'm saying is this whole term goes away, and we get that our limit is just equal to negative 1/4. One more example that I want to show you to illustrate a slightly different point is this function right here. And this function looks a little bit different from this function. In fact, if you look at this, you might note that both of the endpoints, both of our bounds of integration, are perfectly fine over here. Right over here, 0 was the thing causing a problem with this function. Over here, you plug 1 in, no problem. Right, 1 minus 2 is negative 1. Negative 1 squared is positive 1. The cubed root of positive 1 is positive 1. This is just 1 over 1. And similarly, if I plug in 4, I can figure this out, and it ends up being some other value. There's no issues with the 1 nor the 4. However, if you try using the evaluation theorem, you'll get an answer, which is kind of dangerous. It'll just be the wrong answer. And the reason you'll get the wrong answer is because this function is discontinuous somewhere in between 1 and 4. Specifically, when my value of x is equal to 2, and note 2 is between 1 and 4, this thing's going to be undefined, because 2 minus 2 is 0, and 0 squared, and then the cubed root of that is all 0, and 1 divided by 0 is undefined. So over here, unlike over here, my issue is not one of the bounds of integration. It's a point within those bounds. So what do I do? Well, I have this great technique that works out perfectly as long as it's one of the bounds of integration where the issue is. So what I can do is I can rewrite this problem as a sum of two different integrals. And note that what I have on this line is equal to what I have this line. I guess I made two changes. Instead of having this in radical notation, just because it's so hard to deal with, I wrote it in exponent notation, or at least now I did. And so I said it's x minus 2 to the negative 2/3 power. Negative because this thing's down in the denominator, 2 up in the numerator of the fraction because of the squaring, and 3 in the denominator of the fraction because I'm taking the cubed root. And the other thing I did is I split it up into two different integrals. And that's really the new idea for example 2. If you think about this as asking the question, how much area is there underneath this curve from 1 to 4? Well, that's going to be the exact same as how much area is there underneath the curve from 1 to 2, and then also from 2 to 4, and then add up those two answers. Right? The area from 1 to 4 is the same as the area from 1 to 2 plus the area from 2 to 4. And the nice thing about breaking this one problem into two separate problems is each of these two problems in red can be attacked the exact same way we did this problem in green. The 2 is what's causing the issue here. So what I'll do is I'll replace all the 2's, the 2 up here and the 2 down here, with constants. B and A is the standard. Typically you use B when it's the upper bound of integration and A when it's the lower bound of integration. And then what I'll say is I'm just going to figure out the limit as that B approaches 2 from the negative side in this case, right? Because I want to keep the discontinuity outside of this interval. So 1 to a little bit less than 2, if you want to think about it that way, won't include 2. And then here I want A to approach 2 from the positive side, so a little bit more than 2 up to 4. But by making these limits, B approaching 2 from the negative side and A approaching 2 from the positive side, I end up getting all of the area from 1 up to 4. So now you have, I don't know, more or less the same problem to do twice. The good thing is to figure out the antiderivative of this guy. We don't need to use an advanced technique like integration by parts. We can just use the power rule here. If it helps, you can do a u substitution where u equals x minus 2. But because du would just be equal to dx, we don't really even have to write it out. You could probably do it on a one step and just say that if we add 1 to this exponent, we get positive 1/3. But then we have to multiply by the reciprocal of that positive 1/3. So we'll get 3 times x minus 2 to the positive 1/3 power that needs to be evaluated from 1 to b. And since this is the exact same function, its antiderivative is the exact same. I just need to evaluate this one from a up to 4. So for this first one, if I change the x's into b's and then change the x's into 1's, I get these two expressions because 1 minus 2 is this negative 1. And I want to subtract those two guys. And this will work out pretty nicely if b is getting really, really close to 2. 2 minus 2 gets really close to 0, and the cubed root of 0 is just 0. And 3 times 0 is 0. What I'm saying is over here, I just get 0 minus the cubed root of negative 1 is negative 1. And you're like, whoa, I thought you couldn't take the root of a negative. Can't take the square root of a negative. But the cubed root of negative 1 is no problem. It's negative 1, and that's because the thing that you would have to cube to get negative 1 as your answer is negative 1, because negative 1 times negative 1 times negative 1 is negative 1. That was probably really confusing. My point is just negative 1 to the 1/3 power is negative 1. So negative 3 times negative 1 is positive 3. And then similarly over here, I use the evaluation theorem to plug 4 and a into this function. And when I plug in 4, 4 minus 2 is 2. So I got this minus, and then when I plug in a, I get this expression. But sort of the same thing happens. The limit as a approaches 2 from the positive side. If a gets really, really close to 2, 2 minus 2 gets close to 0, cubed root of 0, again 0, negative 3 times 0 is 0. So what I get over here is just 3 times the cubed root of 2. So my final answer here is just 3 plus 3 times the cubed root of 2. Or if you feel like factoring out a 3, we can rewrite it as 3 times, and then 1 left over from this one, and cubed root of 2 left over from this one. So 3 times 1 plus the cubed root of 2. This might not have been a great example because I think if you had done this one without noticing that you had the discontinuity and just used the evaluation theorem, you would have gotten really lucky and things would have worked out. I think you would have gotten the exact same answer, but generally speaking, that's not the case. Generally speaking, if you don't break these up into integrals and evaluate them like this, you can get the wrong answer. Your book gives you a good example of that in example 7 here. So kind of same idea. They go from 0 to 3 of 1 over x minus 1. And maybe you note that x minus 1 is a discontinuity. So you got to break it up from 0 to 1 and then 1 to 3. And then you do the same limit things that I just described in this video. And when you do all this, you figure out you get negative infinity as the value of this limit. So you figure out that it's divergent. But then they give you this big warning. Warning, if you didn't notice this asymptote and just did it using the evaluation theorem, you would have gotten the natural log of 2 as your answer rather than getting this divergent answer. The point is just you want to be able to notice that these are improper integrals, even if me, your teacher, picked a bad example here and gave you one where the answer that you get, even if you didn't notice that, just by dumb luck, ends up being the same as the answer that you get when you go through all this work.